Next we have exercise 8. There are two parts. In part A we are given two sets A1 and A2 which are both well ordered with respect to these two respective ordered relations, the first less than and second less than, and they are disjoint. Okay, so there is no common element. Now using these two ordered sets, we are defining a new ordered relation, on the union of the two sets like this. You take two elements A and B from the union, we would say that A is less than B with respect to the new order or new relation. Actually, I don't want to say that it's an order because that's what we have to show. So let us just call it a relation. So the definition is this: A is less than B under the new relation if either A and B both belong to A1 and A is less than B in A1, that means with respect to the order relation that we have in A1, or both of them belong to A2 and A is less than B in A2, or A belongs to A1 and B belongs to A2. So we have to prove not just that this is an ordered relation, but actually it's the well ordering of the union. That is part A. And in part B, we have to generalize part A from two sets to an arbitrary family of disjoint well-ordered sets, and the family should also be indexed by a well-ordered set. So let's see the solution. So this is the solution to part A. The task of showing that the new relation is really an ordered relation actually is quite easy and straightforward. So I am leaving that to you. So you try it, but if you don't get, please write in the comment section below. Then I will do it for you or give you some kind of hint. Instead, let us now show that this is well ordered with respect to that order, assuming that it's an ordered relation. So for that we have taken a non-empty subset of the union, let's call it B. Now two cases arise. The first of which is that B does not intersect A1. Because B is already contained in A1 union A2, if this is the case, if B and A1 are disjoint, then B has to be entirely contained in A2. Now A2 is well ordered with respect to that 2 order. So B being a non-empty subset of A2, now we will have a least element. Let's call that least element B. To emphasize that this is with respect to the order relation on capital A2, we have written with respect to this. What does it mean? It means that if you take any element C from B, then C is greater than or equal to B with respect to that relation. However, note carefully that for any such C, B and C both belong to A2 because they are inside B and B is now contained in A2. So by the definition of our new relation, this will also happen. B is less than or equal to C for all C belonging to B with respect to the new relation. And that is why B becomes the least element of B or smallest element of B with respect to the new relation. So in this case, we have found a smallest element of B with respect to the new relation. But there is that other case where B and A1 are not disjoint. Okay, so they have some element in common. So if that is the case, then B intersection A1 itself becomes a non-empty subset of A1. And A1, just like A2, is also well ordered. So this non-empty subset will have a smallest element with respect to the order relation on A1. Let's call it B prime. Okay, so what does that mean? It means that for any C belonging to B intersection A1, B is less than or equal to, I made a mistake. A small mistake, but it's mistake means I did not, I skipped steps. This is with respect to this relation. However, now you cannot just immediately conclude, like the previous case, that then B prime is less than or equal to C with respect, I mean you can, but that alone won't tell you that B prime is the smallest element of B, because it's not. It is not means it's not apparent that this will be the smallest element of B, because it is actually appearing as the smallest element of B intersection A1. Will it really be the smallest element of B? Let's see. So let us first write the consequence of this alone. Okay. What does this mean? Just like that part. This means that B prime is less than or equal to C with respect to the new relation for all C belonging to B intersection A1. And now next we want to show that this B prime actually is the smallest element of B. So to compare it with all the elements of B, we choose any element D in B. Now two cases arise. If D is actually in A1, see, as an element of B, D may or may not be in A1. If D is in A1, then obviously D belongs to B intersection A1 because D is already in B. So in that case, you can use this. And by that, we have B prime less than or equal to D. But say D is not in A1. In that case, D is forced to be in A2. But now note the fact that B prime is in A1 because B prime is the smallest element of this, means it's an element of this. So being an element of this intersection, B prime is after all in A1 also, besides being in B. So B prime is in A1 and D is in A2. So by the third condition of the definition of our relation, B prime will be less than D. So that way, actually B prime is less than or equal to any element of B with respect to the new relation. So that is why in this case also, we have found a smallest element of B with respect to the new relation. And that's how our set A1 union A2 with respect to the new relation is well ordered. That is part A. Next, let us see part B. So this is part B. Here we start by considering a family of sets. So I have written a family A, script A. The elements in this family are disjoint well-ordered sets. In part A, we had a family of two disjoint well-ordered sets A1 and A2. Here it's an arbitrary family. The size of this family is determined by the size of the index set J. So you understand that this is an indexed family, and what that means is that for each index alpha coming from J, there is a set A alpha, which is a well-ordered set, and taken together these sets are mutually disjoint. Any two distinct sets from this family are disjoint. Okay. And the order on A alpha which makes it well ordered, say that is this order. To denote it, we use this suffix alpha. It indicates that this is the order on A alpha. What else do we need? It's an indexed family indexed by a well-ordered set. So the index set J is also well-ordered with respect to, say, this order. We can assume one more thing without loss of generality, that the index function for this family is injective. What is indexing? Index function means what? Or indexing function means what? An indexed family of sets is actually not simply a collection of sets. Strictly speaking, it's a function whose domain is J and whose codomain or range, whatever you want to call it, is a collection of sets in which those A alphas are there. and the function does what? It takes an index alpha as input and gives A alpha as output. That is injective. That means for distinct indices, distinct labels alpha, so you take two distinct indices alpha and beta from J, the corresponding sets A alpha and A beta are different. Okay, that's what we will get if we assume that the indexing function is injective. And it makes sense that we can assume this because after all we are going to consider the union of these sets. So if originally this indexing function was not, that is you were not injective, say you are working with a family of sets like this, where for some indices which are distinct but their corresponding sets A alphas are the same, then taking the union of those same A alphas, you don't really get anything new. I mean, you would get the same thing if you consider that A alpha only once, and that is why that would be unnecessary. So we can assume this to be injective. Now what shall we do? Now we are going to define a relation, a new relation on the union of these sets, just like there we defined a new relation on A1 union A2. And we will prove that it's a well-ordered set with respect to the new relation, the union. Let's see how this can be done. So the definition of the new relation on the union of these sets, let's call the union A, is this, and we are denoting the new relation like this, less than star. So you take two elements A and B from A. We would call A less than B with respect to this relation if A and B belongs to some A alpha, same A alpha, same set of our family for some alpha, and within that A alpha, A is less than B. That means A is less than B with respect to this ordered relation that we have on A alpha. If that happens, then we would say that A is less than B with respect to the new relation. That's the definition. However, that may not be the case because in the union, from the union we are taking A and B, so they may belong to different A alphas also. In that case, say or, that is why another condition is there, A belongs to some A alpha and B belongs to something else, some other set of the families, say A beta, for some alpha and beta in J such that alpha is less than beta, and this relation is the relation that we have on J. If that happens instead of this, then also we say that A is less than B with respect to the new relation. Now again, it's despite how complicated it looks, actually it's very easy to show that this is really an ordered relation on A. So this part is also left to you. And now, just like part A, we are going to show that this is well ordered with respect to this. Let us show that next. Okay, so we start this part of the solution. We want to show that our A is well ordered with respect to less than star. So we have taken a non-empty subset B of A. Then, now watch this thing carefully. You can see a set here I, which I have called I. What is this set? It is the set of those indices alpha in J such that B intersects A alpha. That means this intersection is not empty. And this set I itself is a non-empty subset of J. The fact that it's a subset of J, of course, is clear because it consists of some elements in J. Why is I non-empty though? You see, B is a non-empty subset of this A. What is A? A is the union of all the A alphas. So if B is lying there somewhere in that union and B is non-empty, B of course has to intersect at least one A alpha. Otherwise, if it is inside the union and it is not intersecting anything, then how can it be non-empty? Because it is non-empty, that you will have some element in B. That element has to lie somewhere, no? So it has to lie inside A, means it has to lie in at least one A alpha. And that is why the set of indices alpha for which B intersects A alpha itself is non-empty, a non-empty subset of J, and that set we are calling I. Now J itself is well ordered with respect to this order relation. So I, being a non-empty subset of J, will have a smallest element with respect to that order. Let C be that smallest element of I. We won't write, every time we won't write with respect to this order, with respect to that order. It's understood what the order is in a given situation, so that will be there in the background. Alright. Now C belonging to I, C is the smallest element of I, means C after all is an element of I, which means what? That B will intersect AC. That means this intersection is not empty, but at the same time it's a subset of AC also. And AC is well ordered. Actually every A alpha is well ordered. AC is well ordered. So this non-empty subset of AC has a least element, let's call it B. With respect to this, I have just simply written to remind us of the fact that it's there in the background. Now let us choose any element B prime in B. Okay. Having this is of course not enough to declare that B is the smallest element of B with respect to our new order less than star. So we have taken any element B prime in B. Now we want to show that B is less than B prime. Oh, and also the fact that B prime is different from B. Now two cases arise. If B prime belongs to AC, B prime as an element of B may or may not belong to AC. If B prime belongs to AC, then of course using the fact that B is the smallest element of this with respect to the order that we have on AC, we get this. B is less than B prime with respect to this order. However, in that case, B and B and B prime both belong to the same AC, right? Why? Well, the condition here is that if B prime belongs to AC, but B is already in AC because B is coming from here, and that is why by the definition of this new order, in this case B will be less than B prime with respect to the new order. Actually this is what we want. However, we may also have this, no? B prime may not belong to AC. If it doesn't belong to AC, because B prime after all is in B and so is somewhere in A, it will belong to some other A, say A D, for some D belonging to J which is not equal to C. Now what? Let's see. So after that we write this. Since AD intersection B is non-empty. Why? Because our B prime is in AD and B prime of course is also in B, and that is why D belongs to that set I of indices, okay, which consists of this type of indices alpha for which A alpha intersection B is non-empty. Now note that C is the smallest element of I and D is also in I, but D is not equal to C. So C will be strictly less than D with respect to this relation that we have on the index set J. However, now note carefully, You go back to the definition of our this new relation, the second condition of the definition. The index C is less than the index D. And what else do we have? We have B in AC and B prime in AD. So thus element that belongs to that set with larger index, which is in this case B prime, will be the larger element. The other element in this case is B, which belongs to AC, where the index C is smaller than D. So by that second condition in the definition of this, B is less than B prime with respect to this. So in this case also, B is the smallest element of capital B with respect to this relation. And that is why this is a well ordered set, and that completes the solution. So let me just end the video here itself. There is one more exercise, one more even numbered exercise left in this exercise set. So that we will do next week, and then we will straight away start actual topology. So that will be all for today. See you tomorrow with something new. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.